For this last section of notes, we're going to look at a few other slightly more complicated applications of using trig functions to find missing values. A couple reminders for the examples we'll be doing. Don't forget that even though with our unit circle we start our angle measurements from the right by saying 0 and we measure counterclockwise around, for a bearing we actually start from north being 0 degrees and then they measure clockwise. Other important facts are that the angles in a triangle add up to 180 degrees. So if you know two of the angles, you should always be able to find the third. If you see a linear pair, which means two angles that make a straight line, for example, if you have a straight line, but it's somehow divided up into two different angle measurements, then those angles together have to add up to 180. And finally, if you know two of the sides of a right triangle, make sure you're using the Pythagorean theorem to find the third missing side. So in this first example, we have a ship that's traveling. Knots is for nautical miles. It's a speed just like miles per hour, but for traveling over bodies of water. So from its home port, it's going at a course of 123 degrees. Now remember, from our starting point, we're starting from north and we're measuring clockwise, so that would be 90, and then a little bit farther would be 123 degrees. So it's something like that. And since starting from the north is 90, we can even specifically list out that the difference between 90 and 123 makes this angle right in here 33 degrees, which would also mean that we could find the angle in here if we needed it later on as well. So they travel along this length. If it's going 30 knots, 30 nautical miles per hour, and it travels for 1.5 hours, then 30 times 1.5 is going to equal 45. So now we have one of the sides of what will likely end up being a triangle. Then the ship changes course from this point. So again, you might want to imagine an X and a Y axis here, and it's going to go 213 degrees. So starting from due north, 90, 180, and then it adds an extra 33. So it ends up going at an angle something like this. Now something else that you can note here is that the difference between 123 degrees, which was the line going this way, and the 213 degrees, which is going this way, the difference between those two numbers is 90 degrees. So that means that we have a 90-degree angle right in here. And then if we use our linear pair rule, that means we also have a 90-degree angle on this side of the figure as well. Now they're actually going to ask us what is the distance and bearing of the home port to this ship. So now you can see our triangle drawn in pretty well. And I'm going to go ahead and redraw this off to the side just so it's a little bit easier to see with our numbers filled in. We just found that this length has to be a 90-degree angle. And we said because of the speed and the time that it was traveling in this direction, that the side length was 45 nautical miles. We can do the same thing for the second bearing that it traveled at. It was going the same speed of 30 knots for 2 hours, so that would make this 60 nautical miles. And they want us to find the distance and the bearing of the home port to where the ship ended up. Now to find that third missing side, you should be able to use Pythagorean theorem on this. So you can just take 60 squared plus 45 squared, and then take the square root of that answer. So I'm getting a length of 75 knots for the missing side. For the angle, they want us to find the angle in here based on where the ship started and where it ended up pointing. So I'm going to use one of our trig inverse relations to find that missing value. It doesn't really matter which one you use in this case because I've already determined all three of the sides of the triangle. So I'm going to set up sine inverse of opposite side over the hypotenuse. And again, I'm going to keep my calculator in degree mode for this section. And I got approximately 53 degrees. Now there's one small problem with us listing that as our final answer here, because that was the angle inside of the triangle, But if we look back at our original figure, we have to remember that the bearing is the rotation all the way around, starting from due north. So it's actually that 53-degree piece we found, plus the earlier 123 bearing that the ship already had. So 53 plus the 123 is going to give me a bearing of 176 degrees. So my bearing is the 176 degrees, and the distance is the 75 nautical miles. That would describe the location of the ship. For this next figure, we have several triangles drawn inside. Now, in this particular example, we have the same angles, 15 degrees and 15 degrees, which means the side opposite them is split. It basically means that everything is going to be split on this, which makes it a little bit easier. It's trickier if one of them is 16 degrees and the other one is 32 degrees, for example. So in this case, I can just focus on one piece of the triangle, and that means I can cut this horizontal length in half. So I'm going to deal with a triangle of base 38 and then try to find that height in there. So in this case, I would recommend using the tangent function, since tangent of 15 will equal opposite over adjacent. To solve this equation, all you need to do is multiply both sides by the 38 value. That'll get the y by itself. So the answer I'm getting from that is a height of approximately 10.18 feet was the unit that they gave us here. So we just found the height of the vertical center span. And that's all for the notes today. Thank you.